Hey, this is Steve from the Tech Circuit Group, and in this video we're going to go through the voltage mapping for a really common Whirlpool made dryer that also goes by the name Roper, and it's an electric dryer that is well known by many appliance technicians. However, there are a lot of technicians out there that do not know this dryer very well, so this video hopefully will help promote a better understanding of how this dryer works from a voltage measurement standpoint, given different scenarios. We'll first go through the voltage measurements for normal operation, normal scenarios, and near the end of the video, we're going to go over some failure modes and some of the associated voltages that you would find in those modes. And once you plug this dryer in, you have your L1 denoted in black over here that shows up over here by the BK terminal of your timer and over on the left side of this timer motor. Your L2 shows up over here on one side of your centrifugal switch, and your neutral comes down over here and shows up on one side of your start switch, one side of your centrifugal switch for the motor windings, and also WB on your timer. So you're going to measure 120 volts from here to here, and of course you would measure 240 volts from here to here. Now if you want to go to air fluff, and the dryer's not yet started, this timer contact closes, and that brings neutral down to the right side of your timer motor, which energizes it, and now your timer motor is running. In this case, you would hear the motor running, yet you still haven't pressed the start switch yet. Also, what happens in this mode is that the contact here closes. L1 is going to go straight through here. It's going to go straight through your motor winding, the main winding of your motor, because you don't have any current flow yet. If you have no current flow, there's no voltage drop across the motor. L1 just goes straight through there. And now you have a 120 volt drop right across that start switch, and it's just ready and waiting for you to press that button there. And as well, when you close, when you advance to time dry heat mode, this timer contact closes and brings L1 all the way through here. And again, no current is flowing through this circuit here because that centrifugal switch is not yet closed. Given that, you have no voltage drop across here, and you're going to have 0 volts across that element and 240 volts across that centrifugal switch. Now, once you press this start switch, the moment you press that start switch, yet the motor has not gained enough speed to close the centrifugal switch, this main winding is energized, and also the start winding, both at the same time. This main winding is not enough, as most technicians know, to get this motor rotating. So you need this start winding, which is out of phase both physically and electrically, in order to get the rotation going. And you have that 120 volts there. And once you let go of the start switch and the timers and the motor's running, the start winding is let go, and just the main winding, once the motor's rotating, the main winding can actually keep it going. And so you have your 0 volts here now across the centrifugal switch, because now the centrifugal switch is closed. Once the motor has reached about 3/4 speed, that closes to deactivate your start winding, and as well close your heat circuit from L2 to the right side of your heating element, and then you get your 240 volts across that heating element. Now in this scenario, which is auto dry, this particular dryer uses kind of a little trick. So once you switch over to auto dry, their timer contact switches to this resistor here as opposed to neutral. And now your timer motor, while your heating element is on, has no voltage across it. As long as that heating element is on, L1 is here, and L1 on this side, L1 on this side is equal to 0 volts. That timer motor is not going to turn. Now, when this in this mode, when this operating thermostat finally opens up, what happens is you're going to get 0 volts across here because no current's going to flow through here. You have 240 volts across that, and you're going to get 0 volts across your heating element. And that, which means you're going to have L2 right here. L2 is going to get dropped by this resistor down to about 120 volts with respect to L1, where it was 240. And you're going to get, so this basically acts as a voltage divider between here and here. These are going to be approximately the same resistance. And you're going to get 120 volts across each one. Now the timer motor is running while the heating element is off. So as long as this operating thermostat is open, this timer motor will run. And once it closes, then that timer motor will not run. So that's how the auto dry works on this. Now let's go on to some failure modes here. Suppose you're in time dry and you have no heat, and it's due to a failed centrifugal switch. Well, okay, so this centrifugal switch did not close for one reason or another. It's bad. It's got something caught in it. Everything else is working fine, but now you've got 240 volts across here, and you've got 0 volts across the element. So you've checked your element. You know your element's good. Everything else here is good, and you're not really sure whether that centrifugal switch is bad. So what you can do is simply just use a voltage measurement. If you measure this side of the heating element, and then you measure L2. So just put one lead of your meter on this side of the heating element, the side that doesn't have the thermal cutoffs. There's only two sides to it. And then your other lead on L2, if you read 240 volts, you know your motor is bad, your centrifugal switch is bad, thus your motor's bad. Then you know that you just need to replace your motor without having to take your motor out. Here's another scenario here where you have failed timer contacts in your heat circuit. Right here, a lot of current goes through 30 amps, and this is a really high failure rate point right here. And when that happens, your L2 just goes right through the heating element, and you have no voltage drop here. It just shows up over here. You're going to have 240 volts between R and BK on your timer. All you have to do is just measure that voltage difference between BK and R. And if it's 240 volts, then you know you've got a failed timer. Those contacts right there. Now, if you remember auto dry, this scenario where when the operating thermostat is open and you get voltage across this resistor in this timer, if for some reason you lose this wire here that goes from the heating element to that resistor, which I've seen a number of times, that wire comes off or is damaged, then you're going to have nothing here. This is all floating. You have 0 volts. Your timer is going to have no voltage across it from here to here, and yet your heating circuit is still going to work fine. So the customer complains that the dryer is heating, yet it never stops in auto dry or in time dry. It goes down to cool down. Once it reaches cool down, it just sits there and runs forever. Then you know that you have something going on with that wire right there, most likely. Another scenario, kind of similar, if your heating element opens up, burns out, then you have essentially this is all floating here. You have no voltage on this side. And when this operating thermostat will never open up in this case because the heating element is not coming on. So you're just going to have, actually, this is just going to pass right. You're going to have L2, L1 all the way through here to this side. So you have L1 on this side, L1 on this side. That's 0 volts difference. Your timer motor is not going to run. You're going to have heat. And I'm sure that a lot of experienced technicians have run into this before. The customer complaint is that the dryer will run all night, either in auto dry or in cool down, and it's not heating. So if you get that symptom, it's most likely going to be something on the heating element. I have seen this with shorted elements. If L2 shorts somewhere in the middle to ground, this is opened up, you can have that same situation. Here's another scenario here where you have an open thermal fuse. If you have an open thermal fuse, the voltage from here to here is going to be different. And so when you go to press this start button here, neutral is going to go all the way through the motor. It's going to show up on this side of the thermal fuse, and you're going to have 120 volts from WB to BU. If you have that, then you know you've got either a bad thermal fuse or a bad motor winding. Motor windings don't usually open up, but there is an internal thermal cutoff in the motor which can open up as well. And all this you can check from the console. If you make this check from the console, there's a very, very good chance that you've got you've got an open thermal fuse in that scenario. In this scenario here, where the dryer won't start, is because you have this contact right here is bad in this timer. And if that's bad, then it just L1 never makes it through here, and neutral is going to go all the way through both your start and your main winding through the start switch. Now, this is at the moment your start switch is depressed, and if you were to press that start switch and measure from BU to BK while your timer is in time dry, then you know you've got a bad timer, right? Now, our last scenario here is going to be is if you have a dryer that's running in heat mode, but it has no heat. And the reason is that you've lost your L2 voltage line. If that happens, L1 is going to come all the way through here, go through your timer contact. It's going to go through your operating stat. It's going to go through your heating element, and it's going to go through your centrifugal switch since your motor's running, and it's going to show up over here. There's no L2 to push it back. So you're going to read approximately 0 volts from here to here. And now if the dryer wasn't plugged in or running, you may read some voltage here because when the circuit is not under load, you apparently have some loose connection upstream there that's causing you to lose L2 that would allow some voltage probably to get through if it wasn't under load. But once you put it on load, this low impedance of this heating element supersedes that high impedance of the upstream loose connection and will cause this voltage to be pretty close to 0 volts here. Now, a lot of the mistake that a lot of technicians can make is that they'll measure from here to here, they'll read 120 volts. From here to here, they'll read 120 volts, and they think all is well, and they just move on. Well, you don't want to do that because what you measure here is the same voltage that you're measuring there. If L2 is here, L2 is out of phase with L1, and of course you're going to have a 240 volt difference. But you measure here, you're measuring the same 120 volts that you measured over here. And that can just get technicians confused. And generally speaking, you don't want to involve neutral with 240 volt circuits because it's rarely a factor or a part of the circuit. So those are a lot of the different scenarios, both normal and in failure mode, that in terms of some of the voltages that you'll see on this dryer. Hopefully that's been helpful, and if you ever need to refer to these slides, there's a whole set of them on the techcircuit.org website. You can just download it or just bookmark it, and it'll all be right there. And don't forget to click the little button on the lower left-hand side of the screen to subscribe to the Tech Circuit channel. And thanks for watching.